Alright, so this is my final project for a programming class. Um, this project is basically derived from a question that was from dynamics class. So basically, I made a question that's up in this text box right here, where basically the engineer is trying to determine the minimum height for a summit so that when it goes down the summit, it can go around a loop and be able to stay on the track. And he'll be testing this with 800 with carts ranging from 600 to 800 kilograms in increments of 25. And then he'll also be experimenting with the radius of the loop and the initial velocity at which it leaves the summit. And then in return, it should be able to output a velocity at the top of the loop, and then also the height that the summit should be so that it can complete the part of the roller coaster that it needs to. And then there will be a plot um, that will graph the relationship between the mass and the minimum height. And then you'll be able to adjust these with the initial velocity slider and the radius slider, and you'll be able to see the changes in the graph in real time, and then also see the values that you're putting into the slider in real time. So we're going to be using Newton's laws and the law of conservation of energy to be able to um, calculate these. So basically, like you can see over here on the left, it is the sum of the forces in the um, normal direction, and then the acceleration in the normal direction is equal to what the velocity at the loop is squared over rho, which is essentially the radius of the loop. And then we'll just be in the code, we'll be manipulating the equation to solve for this value, the velocity in the loop, and then similarly for the conservation of energy equation, this first h is going to be the height where the initial velocity is. So that's what we're going to be isolating right here. And then this height is going to be the height of the loop, which will compensate accordingly with the code. So I'll look into the code now. So we have three inputs right here, and then there's going to be two outputs, and then two sliders, and there's like four edit fields, and then the plot button. So I'll just look into that. So for the first one, we have the initial velocity or input box. So that'll be that. Um, when you press this calculate button for the initial velocity, or the velocity at the top of the hoop. So we'll assign all the variables accordingly, and then um, like I said, we isolated the velocity at the loop, and we came up with this equation in order to do that. So it's the radius, and then the normal force, and then the weight is actually the mass times the acceleration due to gravity. So that's what that is right there in the Newton's laws, and then divided by the mass, take the square root of all that, and then now we'll get you the output, and then the value that comes into this is assigned to the same variable as what we're going to be putting into that edit field, which will be outputted into this box. And then same thing, similar to that is in the minimum height box. Besides, um, um, we use the same equation because we need the velocity of the loop to be in there to make our conservation of energy equation work. So we have that. And also I said that we needed to compensate for the height in the second part of the equation. because we needed the height of the loop. So whatever will be inputted into the radius of the loop will be multiplied by 2, and then that's right here into that equation. So, and then again, we have that assigned to the same variable as that text box right here, which will pop up in this right box. And then for the plot button, again, I had to assign all the variables, but the main difference being that I had to assign, or instead of taking the value from the drop down box, I made the mass a vector. So it's again the same thing as it's in the increments of 25, just like the drop down box, but we needed to put it in a vector form so that we could use a for loop right here in the bottom. So we use the for loop to be able to calculate the conservation of energy values, or the height value using the conservation of energy um, equation, and be able to do that with all the masses. And then we used a conditional loop to make sure that if the initial velocity was greater than the velocity in the loop, that it would not plot anything at all, because that shouldn't be possible um, using that law technically. So and then I just made sure to have the grid axis turned on so that you'll be able to see it when it gets plotted. And then there's these two sliders right here. So I basically copied and pasted what was in the plot box. Besides, the only difference was you can actively manipulate the radius or button, or the radius that you're going to be graphing with. So there's that assigned to the same value that is assigned to the same variable that's in the edit field that's beneath it, and similar to the initial velocity. This one right here is assigned to the same variable as the edit field that is right underneath it. And then just had to do the plot command and same for and if loop for those. So a live look into this was actually a real question that was asked in dynamics class with you. So I was able to verify that these numbers came correctly, regardless of what number I used, but this is just one that we ended up using for the problem. So you get these values right here when you use the initial velocity of 3 and the radius of the loop being 7.5, and then the mass being 700. If we were to put these same values into the sliders down here, it doesn't have to be perfect. You'll get the general idea of being close enough to the numbers, but you got the what is it, 7.5? All right, and then at 700, 700. So you would get the 18.27, and it's off by a little bit because it's uh, not perfectly at 3, but close enough. Um, so this is that plotted. If you were to, um, I also had the condition that it should not plot anything if the values don't make sense with because the initial velocity should not be more than the final velocity. So if we put these values, the initial velocity being 10 and the radius of the loop being 5, you get these values. And you can see that the initial velocity ends up being greater than the velocity at the top of the loop. which does not satisfy our conditional loop. So if we go and plot these into the graph, you can already see that it's working, but for the video's sake, I'll put the actual values that we're trying to put in right around there. That's close enough. But you see that it doesn't, in fact, plot anything at all, which is the goal of what I wanted to do with the for loop and the conditional loop and how I wanted it to be graphed. So that basically wraps up how my project works and what I did to make it work. So that will be the end of this video. Thank you for taking the time to watch the video and also teaching the class, because then I wouldn't be able to know how to do this. So thanks and goodbye.